foundations of machine learning. And in particular, we've seen lots of algorithms in the class, right? And we've heard words like generalization guarantees and sample complexity. And we promised you guys that the algorithms that we talked about can be shown to work well on new examples that come from the same source, right? So we talked about these things in the past. Today, we're going to demystify what those things mean. Okay, and I'll actually talk very specifically about sample complexity for a very specific model that we've been talking about throughout the class, namely supervised learning. Okay, but before doing so, I just want to give you just a one-slide overview, bigger picture overview about what machine learning theory is about. Okay, so more broadly. Right, so I guess we are talking about foundations of machine learning. You know, that's why I have this pyramid here for foundations. Okay, and so, right, so what machine learning theory studies, so basically a number of very important aspects of machine learning. So the goal of machine learning theory is to develop and analyze models that help us understand what kinds of tasks can we hope to learn and from what kind of data, and also to help us think about what are the key resources involved, like running time or data, the amount of data that we need to learn. Okay. So the goal number one here is to understand, to develop models for understanding what kinds of tasks can we hope to learn and from what kind of data. Okay, that's goal number one. Goal number two of machine learning theory is to prove guarantees about practically successful algorithms. Like we've seen in the very first lecture, the ID3 algorithm for learning decision trees. It's a practically successful algorithm, and we might be interested in proving when does it succeed and how long, what is the running time of the algorithm, under what conditions it does better than other algorithms, and so on, right? So that we know when to choose an algorithm versus another, right? And that's goal number two. And another goal, actually, and I think this is kind of important and interesting, is so machine learning is a very dynamic field. It's incredibly vibrant. It has changed quite a lot in the last 20 years. Okay, so there are always new learning paradigms, new environment. Like, for example, we have the age of big data right now, so we have to design often new algorithms for new learning paradigms that will meet certain desired criteria, right? And so we need to be able to reason about the correctness of our algorithms and how to trade off the resources involved. Okay, so it's very important to have principles to reason about such issues in order to get useful algorithms. Okay, so this is what machine learning theory does in a nutshell, and so it's very important for the success of machine learning. Now, if you like math, also another nice aspect about machine learning theory is that it is connected to many areas. In machine learning theory, you use tools and connect to many other areas, including, we've seen in the class algorithms, obviously, probability in statistics, we've seen this a lot. Optimization, again, we've seen this. Complexity theory, when you prove hardness of certain guarantees. Information theory, game theory, and so on. So lots of cool connections, right? And so it's very interesting intellectually too. And the field itself is very vibrant, so it has its annual conference, Conference on Learning Theory. Actually, last year the conference was in Barcelona, and I chaired the conference, so that's kind of cool. Right, so it has its own annual conference, and actually even more, actually some of the general machine learning conferences like NIPS and ICML, a good fraction of the works in those conferences are related to learning theory. So for many new learning problems people propose or models that they analyze, they often want to provide some guarantees, okay, so that we can be more confident that they are useful. Okay, cool. So that's just a high-level overview of what machine learning theory is about. Today, as I mentioned, I'm going to be very specific, and I'm going to connect what we've done in the past in the class. And namely, I'm going to talk about sample complexity or generalization guarantees or how to prevent overfitting for the problem of supervised classification, right? This is what we've been talking about so far. That what I'm going to talk about can be easily extended to function approximation more broadly, right? Where the output values might be real values, for example, like in regression, which we've seen last time. Yeah, but for simplicity and just to be concrete today, I'm going to mostly focus on supervised classification And in fact, what I'm going to talk about today, it's only going to be for binary classification, where I have two labels, like spam or not spam. Okay, and right, and basically my presentation will be about sample complexity. I'll define that precisely in a moment. And what I'm going to present is some very basic but core results that stem from the statistical learning theory framework of Vapnik and the PAC model of Valiant. Okay, and in addition to my slides and my presentation, if you want to learn more about this, you can read chapter 7 of Tom's book, which is very nicely written. And yeah, and if you want to see more, come and talk to me, take my learning theory course, and so on. So lots of resources. Cool. And by the way, please feel free to interrupt me anytime, okay? So I tend to speak a little bit fast, so slow me down if necessary. Okay, cool. So we're going to talk about sample complexity for supervised classification, and I'm just going to start with, like, in the next 3 minutes or so, I'm going to do a very quick review what supervised classification is, just so that we're on the same page. I'm sure you're all experts by now, but just to start slowly. Okay, so I'm thinking about problems where basically, here's an example of a supervised classification problem. We are trying to decide to write a computer program to help us decide which email messages are spam and which are not spam, right? And so this is supervised classification because the algorithm uses labeled examples. So in this case, it uses email messages labeled as spam or not spam. Okay, and right, so here we want to write a computer program to help us decide which email messages are spam and which are not. And from the point of view of today's lecture, what is really important is that we really want to come up with a prediction rule that does allow new examples on future data, not only on the training set, obviously. Okay, and you all know this by now. I mean, this is informally the problem, but an example of a problem is an informal definition. Now, in order to design a learning algorithm, the very first thing we have to do is to design a set of features for our problem, right? Like, we have to represent our data by using a certain set of features. And I have here a toy example for the spam problem, right? So here I can use, for example, features based on keywords, spelling characteristics, and so on. And here I picked 5 features, right? And so I have a small training sample of, I guess, 7 email messages. So this is the unlabeled part of my examples, right? These are my features for this example, and this is the labeled part of my example. For example, this example is not a spam email. Okay. Right, and now so let's assume that this is, right, this is our training set. Now, given this very simple training set, if you think about it for a second, and moreover, if you think about yes here as being, like, if you think about yes as being 1, and that no as being 0, right, on versus off, right, then you can just quickly verify that, for example, oops, let me go back. So for example, you can verify that this rule over here, which is we're going to predict spam if 2 times money plus 3 times pills minus 5 times known is greater than 0. So you can verify that this rule, right, that predicts spam if this quantity is greater than 0 and not spam otherwise, you can verify that this rule perfectly classifies our training set. Okay? And I'm sure that you guys know by now, because you've seen linear separators a lot. You can also notice that this is actually a linear separator, right? So this is a very specific decision rule is basically given by a linear separator, a linear decision surface. Yeah? And so this could, for example, this could be something that maybe the logistic regression algorithm that we talked about might output on this set of training samples. Okay? Now, of course, you guys know that now we care about not only doing well on the training set, but we also, what we really want to do is to do well on new examples that come from the same source. That's our true goal, right? And so that's actually a good moment to just basically mention again, we've mentioned this several times, but I'm going to mention it one more time. It's particularly important in today's lecture. So I want to mention again that the 2 core questions that we care about in machine learning are the following. So the question number 1 is the algorithm design question. Okay, so we've studied this a lot. What this is about is how can we automatically generate rules that dwell on the training set. So how can we come up with fast algorithms that come up with rules like this one here that do well over the training data, right? And we've seen quite a few algorithms by now. Okay, so that's question number one, and so the algorithm design question, and there are a variety of algorithms in machine learning, and we've already seen some of them. We're going to see more in the future. Okay, so this is question number one, and question number two, and this is equally important, and this is what makes machine learning different from algorithm design. Yeah, so the question number two is confidence bound or generalization guarantees or sample complexity. Okay, which means what this is trying to understand is how much data do we need to see in order to be confident that if we find a rule that does well over our training set, then that rule will also be doing well in the future or new samples coming from the same source, right? So in other words, how many training samples do we need to see in order to be confident that if we optimize over our training sample, we find something that is good overall? Okay, so that's the sample complexity question. It's a core question in machine learning, and this is what really makes machine learning different from algorithm design. If you're a computer scientist, you can think about it that way. Okay, and and just to mention this, so like the very first question is so the key resources when you think about that, especially in the context of supervised machine learning, there are two key resources to think about, and the first key resource is computation, like how much, this is the computation. Like we want to minimize the running time of our algorithms in that context, right? That's the first key resource. And the second key resource is the amount of data, right? And this is related to this confidence bound or generalization guarantees question. So I obviously, ideally, would like to find very confident rules by using, or very good rules by using as little data as possible. Okay, so that would be ideal. Right, and basically our lecture today will be exactly about this question, generalization guarantees or confidence bound. And so this is it's a well-studied question. It has been studied since the 70s in probability theory and empirical processes. It has in very deep math, really cool mathematically. I personally like it a lot. Okay, now for today's lecture, I picked something very basic but core. But, I mean, if you understand what I'm going to talk about today, which is very, very basic, you're going to get a feel about what the field is about. And everything else is details, mathematical details. Okay? So, good. Right. Okay, and I guess before going on, maybe you can guys make a comment, or maybe I'll just mention it. So, to even talk about this second question here, right? To even talk about confidence bounds or generalization guarantees, we need a formal model, right? Because we need to know, we need to set out a precise model on how the learning algorithm interacts with the human expert, right? What kind of data can the learning algorithm get, right? What kind of questions can ask the expert and so on, right? So we need a formal model. Okay, and there are a variety of models that one could consider. Today I'm going to talk about the most basic one, which is kind of really what we've been talking about so far, passive supervised learning. But there are many other extensions for other scenarios. And if I have time, I'll comment about it at the end of the lecture. Okay, so let me start with the most basic model, which is actually really what we've been talking about so far implicitly. Okay, so it's, so we have a distributional learning scenario. Right? So we assume that, let's again think about spam detection, right? Or spam classification, right? So as a problem to think about. Okay, so in this case, we have a distributional learning scenario. So we assume that there is some distribution over our examples. So for example, some distribution over the spam messages, right? Over all possible spam messages. Okay, so there is this fixed but unknown distribution over the data. And now we assume that in the training process, first, a random sample, a small random sample from this distribution, right, of examples is labeled by an expert. So for example, for the spam detection problem, an expert will going to sit down and label a small set of examples as being spam or not spam. Okay. And then this set of labeled examples are given as an input to a learning algorithm, like naive Bayes or logistic regression or SVM or AdaBoost, some other algorithms we're going to talk about later in the course. Okay? And then the goal of this learning algorithm is to come up with a hypothesis function with a classifier. And this classifier could be, of various kinds. Can be, for example, a linear separator if we run logistic regression, or it could be a decision tree if we run ID tree, right? But the key point is that we want this classifier to be a good classifier for future data. for new examples that come from the same underlying source. Okay, so this is pictorially the distributional learning scenario, which is captured by the two models that I mentioned, the PAC, model evariant, and the statistical learning theory framework of Wapnick. Okay, so let me write this a little bit more. So I'm going to start with pictures and make it a little more and more formal. Okay, so let me let me also use words for the same thing, right? So basically in these models, we assume, so in these formalisms, we assume that there is some underlying distribution over the set of possible examples. And we assume that in the training phase, first, a small random sample of these examples are labeled according to some fixed but unknown target function. Okay, so, right, so in particular, we assume that the training sample that we get to see, right, looks like this. So I get example x1, label of x1, example x2, label of x2, and so on, example xm, label of xm. And what is important is that we assume that these examples xi, right, so our examples are independently and identically distributed coming from the underlying source. Okay, so they're independent, each of them, x1 is independent of x2, independent of x3, and so on. And they're identically distributed because they all come from the same underlying distribution. Okay, so we assume that basically our training set is an IID, I'm going to call it IID, training set of examples. Okay, so that's what we assume, right? And I mean, what the learning algorithm could do, so this is a training set, right? This is the terminology I've been using so far. This is our training set of examples. And what the learning algorithm could do is just do some optimization over the given training set, right? Like maybe run the logistic regression algorithm over the training set, right? But what we really care about is to find the hypothesis that will do well on new examples that come from the same source. So a hypothesis that has small error rate on a new example that comes random from the same source. Okay, and just to be, okay, so I guess I can go for last time slowly through the model. Okay, and then, right, so let me use my pen. Okay, I'll define in a second what the error rate is because that's key. Okay, but let me recap again the key elements. So we have a feature space or an instance space, right? And each example is represented by a set of features, right? And we also assume that there is a distribution D over our instance space, okay? And we assume that in the training phase, the examples that we get are examples that look like this. So right, we get to see examples xi that are drawn IID, independently, identically distributed from this distribution D, right? And we assume that these examples are labeled according to a fixed but unknown target function. Okay, we don't know what it is, but they're labeled according to that fixed unknown target function. Okay, and for today's lecture, I'm also going to simplify, and I'm going to assume that that the labels of my example, so I'm going to assume that my target function is a very simple target function, is a binary classifier, right? So the label is either +1 or -1, like spam or not spam. Okay, so that's a scenario. And as I already said, then what we want to do is to do some optimization over our training sample S, and we want to find the hypothesis that has small error rate with respect to the hidden unknown target function and the hidden unknown distribution over the instance space, right? That's what I care about. And so formally, what is the error rate of a hypothesis? Okay, so there are various notions of error rate which we consider. The most classic one, the most widely used one for supervised classification is the one that I have here on my slide. So this is called the 0-1 loss or the classification error loss, and it's very naturally defined as the error rate of my hypothesis. So if I have a hypothesis H, so this is a new proposed classifier, right? Then the error rate of H is the probability that that hypothesis H predicts differently from the target function on an example that comes at random from the same underlying source B, from the same source from where I got my training samples. Right? So that's the notion of error rate that we really care about. So our goal is to do some optimization over a training sample, and we want to find a hypothesis that does well on new examples that come from the same source. So, yeah? So is the notion clear? Yes? Great. Okay, so it's clear. Let me also give you a pictorial representation, because maybe some of you like to think about pictures. Okay, so in this picture over here, let's assume that the rectangle here is my instance space, like my feature space. Yeah, and I can represent the hypothesis by using this basically ellipse over here, right? So this is my hypothesis H, right? I can think about if I'm inside that ellipsis, I predict plus, otherwise outside I predict minus, right? And similarly, that's my proposed hypothesis, right? And this is my target concept C star, right? Again, if I'm inside, where I'll predict plus, outside I'm going to predict minus, okay? Now, if you think about it from this point of view, then what is the error rate? And let's assume that we have a distribution over the instance space. So each point has a weight, right? And if I think about it pictorially, then what is the error rate here of my hypothesis H with respect to the target function C star and the underlying distribution? Yeah, so it's exactly the probability mass of the regions, right, where the two classifiers disagree. And you just, yeah, I'm rephrasing what you said, right? Okay, and what is in our picture the part of the instance space where the two classifiers disagree? Well, so if a point falls outside the union of these two, to use your words, right? So if it falls outside, then so if a point falls here, then they both predict minus, so they agree, right? If a point falls in their intersection, they both predict plus, so they agree. So really, they will predict differently in these regions, right? In this symmetric difference. In this region, they'll predict differently. Here, H will predict plus and C star will predict minus, and also in this region. This is where C star will predict plus and H will predict minus, right? So that basically, pictorially, the error rate of my hypothesis H with respect to the target function C star and the underlying distribution D is the probability mass in this shaded red region. Right? The probability mass of the two classifiers disagree. Okay, cool. So that's a notion of error rate that we're going to consider throughout the course. Okay, and again, the goal is to use my training set, drawn at random from the underlying source, and I want to find a classifier that has small error rate in this sense. Okay, that predicts that, yeah, good. Now, okay, so I have almost all the elements to talk formally about the sample complexity statement. There is one key point that I still need to add, okay, in order, and this is something that Tom actually explained a little bit in the very first lecture. So in order to hope to get any generalization guarantees, I need some inductive bias. I need some prior knowledge. Well, in particular, if my target function can be anything, if I have no prior assumption, then there is no way to get any generalization guarantees, right? So we need, in order to talk formally about generalization guarantees, we need a bias because there is no free lunch, right? And so basically, this is a picture, I stole it from Tom's slides, right? So he had this picture in the very first lecture, number 1, where he was explaining that decision trees can represent any Boolean function. And because decision trees can represent any Boolean function, if I allow my target function to be any decision, arbitrary decision tree, then basically, unless I see all the examples in the world, I cannot achieve perfect accuracy. I mean, there will always be two classifiers that disagree on the label of the examples I didn't see, so I cannot have small error rate. I cannot learn the target function. And this is true even if I want to be just close to the target function. I mean, there are two models. You could imagine trying to find exactly the target function, or you could imagine trying to be close to the target function. Even if I want to be close to the target function, if the search space, if the classifier that I consider are all the decision trees, then that's impossible. You can show. Okay, so we need to add a bit more, we need to add an inductive bias. And what Tom was describing in the first lecture, in lecture number 1, for decision trees, what we might want to further assume is that my target function is a small decision tree. Okay, that will be like a prior knowledge that we use. And then we could hope to learn from a smaller number of examples. Okay, so is everyone happy with this? You guys all connect me? Yeah? Great. Okay, so that's a picture from lecture number 1. So the key point is, in order to hope to achieve any type of generalization guarantees, we need some inductive bias, we need some prior knowledge. Okay, and in the And the way we're going to describe or express this prior knowledge in what I'm going to talk about today in this theory model, so the way we're going to describe this is by considering fixing a hypothesis space H whose complexity is not too large, really. I mean, right? So for example, I can think about the hypothesis space H as being the class of all decision trees that have polynomial size. That's an example. Or it could be the class of linear separators, or the class of decision surface of degree 2. Okay? But I wouldn't want to have H to be the class of all Boolean functions. Okay? So that would be useless bias. Okay? So I'm going to fix a class of functions, and somehow intuitively I'm going to think about this complexity as not being too large. Okay? And this will allow me to hope to achieve some generalization guarantees. Cool. And so I'm going to fix the hypothesis space H. So for the lecture today, this will be kind of, you will have to think about it a bit as being a generic set of functions. It can be either decision trees or small size or linear separators, or maybe conjunctions of Boolean variables and so on. It's kind of, can be any of those. The only kind of requirement that I have is that its complexity is not humongous. It's reasonable. Okay, and now there are two cases to think about, and we're going to start with the simpler case, and then we're going to go to the more complicated case. So the simpler case is, well, the realizable case. So in this case, we assume that somehow we are so insightful that we made sure that the target function is in our hypothesis space, is in our search space. So we design good features, and we somehow believe that the target function belongs to my hypothesis space. Okay, so this turns out to simplify the math quite a bit. Okay, but so it's good as a starting point to think about. It's not the most realistic scenario, and that's why people also looked at the more general case, which is called the agnostic case. In this case, we don't assume that our model is perfect, but we only assume that somehow my target function is close to some hypothesis in the hypothesis space H. It might not be quite identical, but somehow it's close to that, in a certain sense. And then in this case, my goal would be to somehow compete to get as close as possible to the best hypothesis in the hypothesis space H. Okay? All right, so that's the realizable case, which is what I'm going to first talk about, is when the target function truly belongs to my hypothesis space. And the agnostic case is when I only assume that the target function is close to some hypothesis in the hypothesis space. Okay, so while I set up the model, I do a lot of talking, but once I start going to some more specific results, you guys will have to help me, so you'll have to interact. Okay. All right, so that's the setup. Okay, so let me just quickly recap it. So we have a feature space, we have a distribution over the feature space. In the training phase, we get to see examples that are drawn at random from that source, examples xi that are drawn id from this fixed but unknown distribution over the instance space. They are labeled according to some fixed but unknown target function C star. And the goal of the algorithm is then to do some optimization over our given training sample in order to output a hypothesis whose error rate is small, a hypothesis that is as close as possible to the target function on a new sample that comes at random from the underlying distribution. Okay, and again, I already mentioned this, and I described it even pictorially. The notion of error rate that we are talking about is this 0-1 loss or misclassification error rate, which is just defined as follows. The error rate of a proposed classifier H is just the probability that my classifier predicts differently from the target function on a new sample drawn at random from the same source, or coming from the same source. Okay? Now, so what I really care about is coming up with a classifier that has small error rate, right? But that's something I cannot measure because I don't know the underlying distribution. And I don't know the target function, obviously. I mean, if I knew it, I wouldn't do any learning. I would just be happy, right? So I want to find a classifier that has small error rate with respect to the underlying distribution, the hidden unknown target function. But that's something I cannot really measure, obviously, right? If I propose to me a classifier, I cannot measure its error rate. I have no idea how to measure it, maybe exactly. Okay, but instead what I can measure, there is something I can measure. I can measure the error rate of a proposed classifier on the training sample. Okay, and by this I mean I can measure the fraction of mistakes that my proposed classifier H makes on the training sample, right? So I can count up how many mistakes, how many times is my proposed classifier predicting differently from the target function on the training sample, and I can scale that by m, the number of training examples, right? When I get a number between 0 and 1, it's basically, this is the fraction of misclassified examples that H has on the training sample. Okay, so that's something that obviously I can measure, and I can measure this for any classifier I want. Okay, and because remember, my true goal is to find a classifier that has small error rate with respect to the underlying distribution, and because I can only measure this empirical error rate, right? So I'm going to call this the true error rate, by the way, and the training error rate of a classifier, I'm going to sometimes refer to it as the empirical error rate. It's based on what I observed, right? So, I mean, this is the only thing I can measure. In order to hope to output a classifier that has small true error rate, that means that I need to find a way to somehow bound the true error rate of a classifier in terms of its empirical error rate. Okay? If I manage to do so, then obviously, then I can just, there is a hope for achieving my true goal to find something a small error rate. Okay? And this is actually what sample complexity statements are all about. Bounding, relating the training error rate of a classifier with its true error rate. And actually more precisely relating uniformly for all classifiers in our concept space, on our search space, where training error rate with their true error rates. Okay? Because if somehow we manage to relate those and we show that they are arbitrarily close, then we can just optimize for the empirical error rate, and then we are guaranteed that we are doing well overall. Okay, cool. So this is basically the key essence in sample complexity, is what sample complexity statements are about, relating for all classifiers, uniformly for all classifiers, their empirical error rate, their training error rate, with their true error rates. Okay, and actually let me write this down because I'm probably gonna say this. So training error is a name, but another name for this concept here is the empirical error. Okay, cool. So any questions about this? Are these key concepts clear? Yeah? Good. All right, so that's our goal in sample complexity, to relate these quantities. And this is what sample complexity results are all about. And as I mentioned, there is actually an amazingly interesting machinery that deals with this question, like really beautiful math and deep insights and so on. But today I chose to describe a simple statement that is it's actually very insightful. It's very simple to state. It's very simple to prove. And it's kind of the essence of, the beginning of the essence of the whole machinery that I'm not going to talk about. Okay? So I'm going to make a further assumption. So I'm going to now think about actually the realizable case. So remember, what is a realizable case? Do you guys remember what is a realizable case? What do I assume in the realizable case? Exactly. I'm assuming that my target function is in my search space, is in my class of functions. Right? So I'm going to make this assumption. I have a class of functions. I'm going to assume that my target function belongs to that class of functions. And so in that case, under this world, then here is a reasonable learner, so which is what we call a consistent learner. Then what this learner is going to do, what this algorithm is going to do, it's a generic type of algorithm. What we're going to do, we're going to take as input a training set of examples, labeled examples, and we're just going to output a classifier from my class of functions that is consistent with the training sample. So we're going to output a classifier that is perfectly labeled as a training sample. And we know that it will be able to output a classifier, right? Because I made the assumption that my target function belongs to the search space. So there will always exist a classifier that is consistent, gets the training sample perfect. Okay? Yeah?
So in case of consistent learner, overfitting will be a problem, right?
It could be, but I'm going to show to you that in this distribution learning setting, it's not going to be. So that's exactly a wonderful question, perfect for my next statement. Okay? So that's exactly what sample complexity, so I'm going to show a sample complexity statement. We're going to give us a condition on how many training samples do we need to see in order to be confident that if we find a classifier that perfectly labels the training sample, that classifier will have small error rate with very high probability. Yeah, so you might think, well, that it could be a problem if the learner is consistent. But it turns out that if I see sufficiently many examples as a function of the complexity of the search space and the accuracy that I want to achieve, then I'm guaranteed that if I find something that does all over the sample, it's perfect, it's consistent with the sample, will have good accuracy, it will have small generalization error. Oh yeah, and actually let me also go back here because I wanted to, I see that there are these words that I always use. So in addition to true error, sometimes I'm going to call this also the generalization error because this is really the error defined with respect to a new training sample that comes from the same source. Okay, so let me also write this down. It's a key concept, generalization. Okay. My handwriting is not the prettiest, but luckily I'm going to use lots of typed text. Okay, cool. So going back to your question, so your name is Mustafa. Okay, so going back to Mustafa's question, right? So how many training samples do we need to see in order to be confident that if we output a rule that is consistent with the training sample when none exists, so we can then be confident that the rule does well on new examples that come from the same source. Okay, and here it turns out that you can come up with a claim, and this is the basic sample complexity statement that I'm going to prove today, and which is really at the essence of all the subsequent sample complexity statement. Okay, so and I'm going to first say the result, explain a little bit what it means, give an example, then I'm going to go through the proof, and then I'm going to talk about the generalization. Okay, so let me go through the statement slowly. So in the case where, on this statement here, I mean, you don't have to assume for the statement that the target function belongs to the search space, but it only has an implication in that case. Okay, so we might as well think about the case when the target function does belong to the search space. Yeah. Okay, so what this statement says is that let's think about the case where the target function does belong to the search space, to the hypothesis space H. And what this statement says is that if the number of training samples we see in the training process is at least, and there are these quantities over here, 1 over epsilon times log of size of H plus log 1 over delta. Right? So if I see so many training samples, many labeled examples, then we are guaranteed that with probability at least or minus delta, all the classifiers in my search space that have true error rate at least epsilon will be inconsistent with the sample. Right? So we are guaranteed that with high probability at least or minus delta, any bad classifier whose error rate is at least epsilon will make at least one mistake. Right? So we're not going to have perfect error rate on the sample. Okay, so this is what this statement says. Now, what is the contrapositive of this statement? So do you guys know what is contrapositive? You know that if A implies B, it's equivalent to not B implies not A. Yeah? What's your name? Amar. Okay, as Amar said, right? If A implies B, then that's equivalent to not B implies not A. Right? So using the contrapositive here, right, what do I get here? Is that if I see so many training samples, then with high probability, all the classifiers that have empirical error rate 0 will have true error rate at most epsilon. Right? So I also have it here written, right? So basically, the contrapositive of the theorem is that if I see so many training samples, 1 over epsilon times log size of H plus log 1 over delta training samples, then with high probability at least or minus delta, all the classifiers that perfectly classify the samples will have a true error rate at most epsilon, right? So do you guys follow what I was just talking about, right? So if I think about this as being event A and about this as being event B, right? I said what we wrote here is if I see so many training samples, then A implies B. But another way, if I take the contrapositive, then this would be if I see so many training samples, then not B implies not A, which means if I see so many training samples and with high probability, all the classifiers that have empirical error rate 0, right, that's not B, will have true error rate at most epsilon. Right? So obviously in that case, if the target function does belong to the search space, then there will be a classifier that has true error rate, that has empirical error rate 0, in particular at least the target function. And then I'm guaranteed that if I use a consistent learner, then I get good generalization guarantees. Because this theorem tells me if I see so many training samples, any single classifier that will have empirical error rate 0 will have true error rate almost epsilon. And because I assume that the target function belongs to the class, I'll be able to find a classifier that is perfect for the sample. Okay, cool. So that's the statement. Okay, and let me, so to me this always looks very natural, obviously, because I've been working on this for many years, but so let me just go slowly and describe what these quantities mean. So I wanted to make a couple of comments. Because there are these epsilons, deltas, why do we need them, what do they mean? Okay, so let me quickly describe this, okay? So, right, so you see here that I have this parameter epsilon, and people refer to this as being the accuracy parameter, the error parameter, epsilon from error. This is error parameter. And the reason for which we need this error parameter is, conceptually speaking, because, well, imagine that you have a distribution that places a very, very tiny weight on certain parts of the space. Very, very small weight, like exponentially small. Then obviously, unless I see a training point from that part of the space, I'll have no idea what the target function says in that part of the space. Right? And this is exactly the error parameter epsilon is trying to capture. If I have a part of the space whose weight is like epsilon, think about it as being epsilon, unless I see a point there, there is no way for me to know what would be the target function saying there. And in order to see a point there, if the weight is epsilon, I need to kind of see one over epsilon samples. Yeah, so that's the intuition behind this epsilon parameter. Okay? So it's kind of needed. Okay, and also this explains why this behavior is like 1 over epsilon. At least. Okay? Luckily, it turns out that it's actually 1 over epsilon. Okay, so this is the error parameter. Okay, now I also have another parameter here, the delta parameter. And this is called the confidence parameter. And right, so you see the statement is probabilistic. So we are guaranteed that with high probability, at least or minus delta, something good would happen for us. Right, this is what we guarantee. Okay, and you might wonder why not why not always? Why not a deterministic statement? Why do I even have to say with high probability? Well, we have to say with high probability because we're talking about a probabilistic process. The sample is a random sample from the underlying distribution. And there is always, especially when the sample is small, there is always a chance that basically the sample that we get to see is not a representative sample for the underlying distribution. It's a very tiny chance that it will happen, but it might happen. Okay, and this is exactly what the delta parameter is trying to capture. Okay, so that's why we use a high probability statement as opposed to a deterministic statement. Right, because basically the training sample, we are in a probabilistic process, the training sample that we get to see is a random sample from the underlying distribution. There is always a tiny chance that the sample that we see is not really representative for the underlying distribution. And so then kind of we use this delta confidence parameter to talk about the unlikeliness of that happening. Okay? Right, so these are the key concepts in the bound, and also another key concept here is also log size of H. Right, so actually, just to be clear here, this discussion so far, so here I'm assuming that the search space is finite. So I'm already making a restrictive assumption, or an assumption, just for simplicity of the presentation, that the search space is finite. So for example, it could be a decision tree, right, if the inputs are like categorical and the outputs too, right? Or it's not necessarily, it cannot be a linear separator because then we have an infinite number of linear separators. But luckily it turns out that we can extend this to talk about more interesting cases too. Okay, but for now let's think about it as being finite. Okay, and when the bound has the key free elements, namely the 1 over epsilon, this is the epsilon is the accuracy parameter, the error parameter. I keep saying accuracy is the opposite of error. Like accuracy is 1 minus the error. Right, so epsilon is the error parameter here. So the bound depends linearly in 1 over epsilon. So it's inversely linear in epsilon. It only depends, luckily, only logarithmic in 1 over delta. So that means that the delta parameter is easier to handle. I can handle smaller and smaller delta with easier than, yeah? So that's good. And it also depends logarithmically in the size of H. And this is really good news here. So the bound only depends logarithmically in the size of H. So that means that even if the search space is, say, exponential, then I still only need a polynomial number of samples in order to learn well, which is great, right? So that's good news that the bound depends only logarithmically in the size of H. Okay, cool. And now I have an example, and you guys can help me go through the example. Okay, I have the example. Okay, so now finally I get to interact with you. Okay, so let's assume that H is a class of conjunctions over the Boolean cube. So the instance space is the Boolean cube. Okay, and let's assume that H is a class of conjunctions. So, I mean, these look like functions in the following form. So here is a conjunction. H1 could be x1, x3 bar, x5, which this is a conjunction. Which what is this like? What this function says: if the first bit is on and the third bit is off, and the fifth bit is on, then I predict plus, and otherwise I predict minus, right? So if all these three statements, if all these three things happen simultaneously, I predict plus, otherwise I predict minus. It's an example of a conjunction. Okay, another conjunction here is if, another example, x1, x2 bar, x4, x9, right? And similarly, if the first bit is on, the second bit is off, the fourth bit is on, the ninth bit is on, then I predict plus, otherwise I predict minus. Okay? Now, what is the size of this class of functions? So think about, we have n features. 2 to the power of n. So is it 2 to the power of n or even slightly larger? So it's those two, if I only allowed for what we call monotone conjunctions, which means any, so this is called the literal, right? So if if x1 can either be, if I don't allow for negations here, if I only allow for conjunctions of positive literals, then it will be 2 to the power of n. But because we allow for negations, I claim it to be 3 to the power of n. Okay, do you guys see why? So somebody wants to give me a quick proof? Yes?
I know that it's one there, or there's zero there, or get variable without using.
Exactly, right? So basically for every single variable, I have 3 options. Right? So for example, here I do not include x2. So I have an option to not include the variable, right? So there are 3 options. Don't include the variable at all, include it as positive, or include it as negative. Include it as variable or include it as negation. So there are 3 options for each variable. So that's why it's 3 to the n. I have 3 options for every single variable, right? When 3 times 3, 3 to the n. Yeah? Cool. What is your name? So, hi. So what is your name? Botier. Did I pronounce it right now? Okay, all right. Well, I'm trying to learn your names because you guys know my name, but okay, it's harder for me because there are many, but still I'm trying to learn some names, especially of people that interact. Okay, cool. So the size here is 3 to the n, and so basically if I plug into my sample complexity statement, what my sample complexity statement says, well, even if the size of my concept space here is exponential, it's 3 to the n, right? It's exponential in n. Even so, even in that case, somehow, if I only see 1 over epsilon times log of 3 to the n, which will be n times log 3, right? So if I see 1 over epsilon times n log 3 plus log 1 over delta examples, then high probability at least 1 minus delta, what my theorem tells me is that I can be confident that all the classifiers that have empirical error rate 0, that are perfect with the samples, will have true error rate at most epsilon. Okay, so that's nice because the search space, the number of functions we are thinking about is exponential, but the number of samples I need to see in order to get good generalization guarantees is only polynomial in n. So that's nice. Polynomial in n, inversely linear in epsilon, and only logarithmic in 1 over delta. Okay, and so for example, just I don't do this very often, but for the first time when I saw the bound, I did it. So just to plug in some numbers. So for example, if n is 10, if I have 10 features, and if we're thinking when to get accuracy, which is like 0.9, which means error rate is at most 0.1, right? And if I want this to happen with very high probability, with probability at least 1 minus 0.01, right? In order to, so how many samples do I need? Well, if you go through the math, I did this offline, so if you go through the math and you can compute and see that what this bound tells me is that 156, if I see 156 examples, then I can be confident that any hypothesis that is perfectly correct on those 156 examples has true error rate at most epsilon. Okay, so that's nice. Right, for these values of epsilon, 0.1, and for the values of delta, 0.01. Okay, notice also that here, how many samples do I have, how many possible training samples do I have? Because n is 10. 2 to the 10, right, which is 1024. Yeah, so which is much larger than what my bound is asking for. Because I'm only saying I only need to see 156 samples to guarantee that something nice will happen. Okay, so something really interesting happens. It's something meaningful that is going on. Some real learning. Oh yeah, and actually because tau Tom keeps mentioning this in the lecture. So let me also, this is not related to today's lecture, but just really a side question for you guys to think about. So, right, so I mean, for all the classifiers or the type of functions we are thinking about, it's good to visualize them and it's good to have a feeling of what they look like, right? And so here's a side homework question. You might see it in the midterm or final, so it's fun to think about it. So I claim that any conjunction, so right, so any classifier that looks like this, so any conjunction can be written as a decision tree. In fact, as a simple decision tree. It's something called like even a decision list. So any conjunction can be written as a decision tree, and also any conjunction can be written as a linear separator. So, yeah? And then you can also visualize it. Okay, so that's really a side homework question for you to think about. I'm not going to go through it now. But while I was at this example, I wanted to mention that. Okay, cool. And now, this is when the fun part happens. So now I'm going to actually prove the theorem. And the proof will not going to be too complicated. It's just a one-slide proof. And, but it will be a very insightful theorem. So it's simple, but super insightful. So it's kind of the core of sample complexity. So it's very helpful to understand it. OK, cool. And you guys help me prove it, by the way. All right, so again, the statement that we are trying to prove is that, so again, just it's simpler to think about a case where the realizable case, we have a fixed class of functions, it's a generic class of functions, and we assume that the target function, for simplicity conceptually, let's assume that the target function belongs to the class. We don't really need to assume that, but just for simplicity. Okay, and then so what we're going to prove is that if the number of training samples we see is at least 1 over epsilon log size of h plus log 1 over delta, then with high probability at least 1 minus delta, all the classifiers of true error rate at least epsilons, all the bad classifiers will have empirical error rate which is non-zero. So it will be inconsistent with the data. Right, so this empirical error greater than 0 really means inconsistent with the data. They will make at least one mistake. With the data, with the sample S. Okay, cool. Okay, so let's prove it. It has a number of very basic steps, 3 basic steps. Okay, and just for simplicity, just conceptually, it helps for us to think, let's just list the bad classifiers. Let's just list the classifiers whose true error rate is at least epsilon. Right? So we are worried that those classifiers are going to survive, that any such classifier are going to survive. So what we want to bound is what's the probability that any such bad classifier are going to fool me. Right? This is what we want to bound. Okay, and just conceptually, because I want to discard all of those, let's just list them. We really don't have to do this, just conceptually we are doing it, yeah? So I'm going to list the bad classifiers. I'm going to assume that I have k bad classifiers of true error rate at least epsilon, so, and I'm just going to list them. It's easier for me to see them in front of me, okay? Okay, cool. So now, step number 1. So let's just fix now one such bad classifier, right? Let's fix hi, whose true error rate is at least epsilon, right? Now, if I then draw a training sample, so if I then draw a point xi at random from the underlying distribution, I draw the first training sample, so I draw x1, right? And then I'm asking you, what's the probability that this classifier hi is consistent with my first training sample? Well, its true error rate is at least epsilon, so there is at least an epsilon chance that it is consistent with the training sample, right? So then what's the probability that my classifier hi labels correctly this first training sample drawn at random from my underlying source? I'm just thinking about one training sample, right? And just one training sample. I fix hi, and then I draw. I know that its true error rate is at least epsilon, which means I know that if I then draw a point at random from the underlying distribution, has at least an epsilon chance of predicting differently from the target function of that random sample. I know that, right? And so then I just want to do just one simple piece of math to then argue that the probability that hi is actually getting correct with the first training sample is, come on guys, 1 minus epsilon, thank you. Right? Just by definition. Because the probability that is consistent with the first random sample is, the probability that it predicts differently on the first training sample is at least epsilon, so the probability that is consistent is at most 1 minus epsilon. Okay, thank you. Good. So now, given this, then if I then draw more training samples, if I then draw MIID training samples, so I shouldn't have done that. Okay, if I then draw MIID training samples, what's the probability that my classifier will be consistent with all of them? So these are independent redraws, right? So what's 1 minus epsilon to the power of m, right? Right. So because these are independent rows, then I get that the probability that my classifier HI is consistent with all of the first time training samples will be 1 minus epsilon times 1 minus epsilon times 1 minus epsilon, so 1 minus epsilon to the power of m, right? Because these are independent rows. Okay, cool. So that's good, progress. Now, what I really care about, so this is for a fixed HI, right? But what I really care about is to bound the probability that there exists a bad hypothesis that survives, right? So what I really care about is this bounding the probability of this event, of this bad event, that there exists a hypothesis HI out of these bad ones here that somehow is consistent with all the M training samples, right? This is what I want to bound. If I make this at most delta, then I get my theorem, right? Because then with probability of minus delta, I'll declare success, right? So this is what I want to bound. What's the probability that at least one of the classifier HI is consistent with the first M training samples? Okay, but I know what's the probability that if I fix any of them, if I first fix HI and then draw the random sample, then I know that the probability that classifier is consistent to the M training sample is at most minus epsilon to the M, right? I already proved this in step 1. So then now step 2 is asking what is the probability that at least one of the classifiers that exists an HI that is consistent to the M training samples. So how do you bound this? I'm thinking about something very simple, right? So if I have 2 events, because I'm doing something very complicated. I'm asking for something simpler. So you are overthinking. I'm asking for something super simple. So event A1, the bad event A1 is that probability that the first classifier H1 is consistent with the training sample. That's argue minus epsilon to the M. Event A2 is the probability that the second classifier H2 is consistent with the training sample. We bounded that it's 1 minus epsilon to the M. Now it's the probability that A1 union A2 happens.
1 minus epsilon times 3 less than their sum.
It's less than their sum, exactly, right? So if I have 2 events, so let me just write this now, right? So what I want to use right now is if I have 2 events, and I'm going to repeat this m times, I'm going to roll. If I have 2 events A and B, right, and I care about the probability of that A union B happens, probably with at least one of them, right, with these 2 events happens, then that's upper bounded by the sum. Right, so if the events are disjoint, then it will be exactly the sum, but they could overlap, so therefore it's the probability that at least one of them happens is upper bounded by their sum, the sum of their probabilities. Yeah? So then I'm just going to apply this. Okay, so basically by applying this basic fact, I get that based on point 1 that I just proved, I get the probability that at least one of the HIs is consistent with the first M training samples will be 1 minus epsilon to the M plus 1 minus epsilon to the M, and this k times, because I have k possible bad hypotheses, so that will be k times 1 minus epsilon to the M. Right? Right, and by now, so I'm trying to get this to be at most delta, this probability to be at most delta, right? But now I don't know k, because I don't know the underlying distribution. I mean, I just conceptually listed them down, right? So, but what I know for sure is that k is upper bounded by the size of h. It's a super loose bound, but it's a correct bound. Okay, so then I know that the probability that the bad event happens, that at least one of the hypotheses HI is consistent with the first M training samples, is at most size of h times 1 minus epsilon to the M. And what I want to do is to set this probability to be at most delta, right? Because if I did so, then I get immediately my desired result. Okay, and basically what we have to do in step 3 is to calculate the value of M so that we have that size of h times 1 minus epsilon to the M is at most delta. Okay. Now, in order to do so, we're gonna, okay, so I'm just gonna tell you the secret. So we're gonna use basically, this is a well-known, basically it's a simple, easy to prove inequality. You can show that for any x between 0 and 1, we have 1 minus x is upper bounded by e to the minus x. For example, you can do a Taylor expansion, just prove it, easily. So that's definitely a true statement about, it's a true inequality, right? And then if I apply my inequality here, right, so what I want to do is to find the value of m so that this happens. So in order to ensure that size of h times 1 minus epsilon to the m is upper bounded by delta, I want to find the value of m that will ensure that. And by using this inequality, I claim that if I find the value of m so that size of h times e to the minus epsilon m is at most delta, then I'm guaranteed that this will be true. Right? So in order to get this to be true, it's sufficient by using this fact over here to impose the size of h times e to the minus epsilon times m is at most delta. Okay? And so now, but now this is very simple to manipulate expression. So all I have to do is to solve for m. Okay, and so let me just do it. Right? How do we solve this? Right, so, right, how do I solve this? Well, I can just, oops, oh no, what did I do? Okay, good. Right, so I just want to solve quickly for the value of m so that this is true. I want to find O value of m will ensure that this is true. And so what I'm going to do, I'm going to have e to the epsilon m. So I'm going to move things on the other side. Is at least size of h over delta. Right? Okay, and now I take logs. If I take logs, I get that epsilon. So if I then take logs, I get that epsilon times m is at least log size of h, natural log of size of h over delta. Right, this will be size of h over here. Okay, good. And then basically, if I just then solve for this, it's sufficient to ensure that m is at least 1 minus epsilon. So I move epsilon on the other side, right? M is at least 1 minus epsilon. And now, just to write the bound in the form that I had here, I just use the fact about log. So log of size of h over delta, right? Log of a times b is log of a plus log of b, right? And I'm doing this just so that I can better see the key terms involved in the bound. My handwriting is not very good, but I'm trying. Okay, cool. So in any case, by just doing a simple algebraic manipulation, then we just get the promised statement that if the number of samples we see in the training set is at least 1 over epsilon times log size of h plus log 1 over delta, then with high probability at least 1 minus delta, all the classifiers of true error rate at least epsilon will be inconsistent to the data. So we're going to be able to notice them, and we're going to be able to discard them. So they're not going to fool us, which is good because it means that if I see so many training samples, then with high probability, if I output a consistent classifier, I'm guaranteed that that classifier will have true error rate at most epsilon. So I get generalization guarantees, which is cool. Okay? So that's a key result. I mean, it's very simple to prove, but it's truly the essence of how these results are proven. Okay, so here many things are simple, right? Because first of all, I made an assumption that for this statement to be helpful, right? So I need to kind of assume that the target function is in the class, because if I don't find any consistent classifier, the statement will be still true but meaningless, right? So here, this only applies in the realizable case where I truly assume that the target function belongs to the class. So that's one big assumption I made. And I also made an assumption that h is finite, right? Obviously, if h is infinite, like for the class of linear separators have infinite number of linear separators, right? If h is infinite, then I cannot do this simple trick here, of union bound trick here. So I need something much more insightful, right? But that's doable. But from the point of view of getting the feeling of what sample complexity results are about, this statement is essential. I mean, it gets to the core. So any questions about this? Or comments? Yeah?
What's the model of like linear,
if you had linear classifiers,
yeah,
how many? Okay, so we're going to go for the next time. So if we had linear classifiers, then we'll have in that case when h is infinite, we'll have to replace log size of h with a different measure of complexity. And the measure of complexity that turns out to work well, and I'm going to describe it next time, it's something called VC dimension and of the concept class. And for linear classifiers, that will be D. So if we had linear classifiers, my bound will look like, if the number of samples, linear classifiers in RD, right? Then when my bound will look, if the number of samples is D over epsilon plus 1 over epsilon log 1 over delta, then success. Okay? So when the case when we have, when the class of functions is not finite, I need a different measure of complexity, and we'll talk about it next time. But to answer your question, if we were looking at linear classifiers, this will be D, or D is a dimension. Instead of log size of H, I would replace it with D. Okay, so this looks like a very simple to state and to prove theorem, but it's very general, right? Because it works for any concept class. So no matter what is your concept class, as long as it's finite, we have a good bound on how many samples you need to see to guarantee that a consistent learner does well. Okay, cool. And just to make sure that I guess we are all on the same page. Just I have a question for you, right? So my statement is a probabilistic statement. I say with probability, high probability, at least 1 minus delta. What is my probability over? So what's the sample space, right? When you use the word probability, we always immediately think about the sample space. What is the probability over? So is the probability over with high probability over what? What is the sample space? What is random? I guess we can go back to the proof and see what did we use randomness. Right, so what was random here? When we state the model, right, we are saying if there is an underlying probability distribution over the instance space, in the training phase, we first get a random sample, a sample drawn at random from the underlying distribution, right? So the randomness comes from the training sample. So the training sample is, right, we get a training sample of size m at random from the underlying distribution. So the probability is over the different samples of m training examples. Right, so this is what the randomness is over. Is everyone happy with this? Okay, so it's important to keep in mind when we make probabilistic statements and we talk about with high probability or probability over what? So in this case, it's over the draw of the m training samples, right? Because the statement says if I draw m training random samples from the underlying distribution, then with high probability over the draw of the training samples, of these m training samples, then all the classifiers with true error rate at least epsilon will be inconsistent with the data. Okay, so it's good to keep in mind. Okay, cool. And actually, let me, there are a couple of ways to think about this theorem. So the way I stated it is the way, so this is sample complexity result for the case when the hypothesis space is finite, like conjunctions or decision trees and so on. Okay, and this is the statement for the realizable case. It's only used in the realizable case where the target function belongs to my class of functions. And the way I stated it, it's the way it's stated in the PAC model of Eliant. PAC, by the way, stands for probably approximately correct. Okay, and you can see why, because actually if you look at the theorem, what I'm asking is how many training examples suffice so that with high probability over the draw of the training sample, I'm approximately correct. I have a small error rate, right? So that's why this is called PAC, probably approximately correct. Okay, and so the way I stated the theorem is stated in this PAC sense, which is the way to think about it, is how many training examples suffice so that I can guarantee small error with high probability. Okay. Now there is, and this is actually right. It's from the PAC model statement, which is due to Valiant. He's a computer scientist, Turing Award winner, the highest honor in computer science. So if you come up with good models for learning theory, you'll be very accomplished. Good. So. But there is another way to restate the same statement, actually, and this is more the statistical learning theory way of thinking about things. So there is so this was coming from theoretical computer science. There is probabilists or statistical learning theorists. People have been thinking about the same things in parallel. And now let me state the same statement. I mean, basically it's the same proof, but I can just state the statement differently in a statistical learning theory way. And now what I'm going to state is for any value of m, no matter what is m, right? So here what I said in the PAC way of thinking, I'm saying if m is large enough, and the number of samples is large enough, then I can guarantee small error with high probability, right? This is the PAC way of stating the results. Now the statistical learning theory way of stating the same result is for any value of m, no matter what m is, I can give you a bound on the generalization error of any consistent learner. Right? By consistent learner, I mean a learner that outputs a classifier that is perfect on the sample. Right? So basically, what this statement says that with high probability, at least 1 minus delta, again, over the draw of the training samples, over the draw of m training samples, with high probability, at least 1 minus delta, uniformly for all the classifiers h in my class that are perfect on the sample, I have at their true error rate, their generalization error rate, is upper bounded by this quantity, 1 over m, log size of h plus log 1 over delta. So you see, basically the error rate decreases linearly in the number of training samples. So it's kind of useful to think about it this way too, because you can see that the error rate of a consistent learner decreases linearly in the number of training samples. And again, I also have this nice log size of h here as opposed to size of h, right? The right dependence too. Okay, and so basically, this is just a restatement of the statement above. It's another way to think about it. It's also very helpful. So whichever you prefer. Okay, great. So any questions? Do you guys have any questions? Because if you don't have any questions, I'm going to tell you one generalization of this statement. Right, as I mentioned, this is very useful to think about it, and it's great we want for this proof, and I really hope that you guys are going to go through it offline and truly internalize it and understand it, because if you do so, then you are, like, it's awesome. It's good for you, because you truly get the insight of what generalization means. Okay, so definitely I encourage you to think about it carefully offline. Okay, right, so the theorem that we proved is very nice. However, it's kind of restrictive because, as I mentioned, it makes sense when h is finite. Right? And often in practice, I mean, obviously, it's impossible to guarantee, it only makes sense when h, in the realizable case, where the target function belongs to the class, right? Because otherwise, it doesn't make any sense. It doesn't tell us anything useful, right? But often in practice, obviously, I mean, it's impossible to guarantee that the target function does belong to the class, because, you know, we don't know the target function. I mean, most often it doesn't belong to a specific fixed target, specific fixed class of functions, right? So it would be much more interesting to also develop generalization bounds that work even in the more general case, where in the agnostic case, where the target function does not necessarily belong to the class. But then what I want to do is to compete with the best classifier in the class. Right? And it turns out that we can kind of extend these results to handle that case. Right? So if the target function does not necessarily belong to my hypothesis space, then I cannot rely on a consistent learner because I mean, I'm not going to be able to find a consistent, I might not necessarily be able to find a classifier that is consistent with my training samples, right? But what I can instead do, I can obviously still minimize the number of training mistakes, right? I can still minimize the number of mistakes over the training sample, right? And I might still wonder, if I do so, what can I guarantee about the generalization error of the classifier that I output? Okay, and it turns out that we can use a very similar reasoning, and we can get what is called uniform convergence bounds. So in the case where the target function doesn't necessarily belong to the class, we can then get uniform convergence bounds that relate the true error rate with the empirical error rate for any classifier in my concept class H. Okay, so that's called uniform convergence bounds. And here is a bound. So it's stated here. So what we can show, and I only have 1 minute to describe it, and then we'll go from there next time, right? So the bound says, so in the agnostic case, what we can show is that if the number of training samples we see is at least 1 over epsilon, 1 over 2 times epsilon squared, log of size of h plus log 2 over delta. So if I see so many training samples, then with high probability at least 1 minus delta, I have it uniformly for all my concepts in the concept space, where empirical error rate is within epsilon over true error rate, right? So what is this implying? That if I see so many training samples, and if I then find a classifier that minimizes the error rate over the training sample, then what can I guarantee about its true error rate compared to the true error rate of the best classifier? Right, so this bound says, if the number of training samples I see is at least this quantity over here, then uniformly, I can guarantee to you that uniformly for all classifiers in your concept space, the empirical error rate is within epsilon over true error rate. Okay, so let's assume that's true. Well, I promise you that. And then what we do, we find what our learner does, just find a classifier of smallest empirical error rate. So output H, whose error rate over the sample is the smallest. Then what can I say about its true error rate? Well, it's true, yeah? So any? Is it much larger than, yeah? Yeah, but let's compare. Okay, we don't have an absolute value perfect, but we'll do, I mean, okay, I guess what we're going to compete with is the error rate of the best classifier in the class. So let's assume that H star is a classifier that has the smallest error rate in my concept class. Then what can I say about the error rate of the classifier that I output by minimizing the training error as a function of the true error rate of the best classifier in the class? Well, think about it. My best classifier in the class has empirical error rate only bigger than the empirical error rate of the classifier that I output. Right? Because I'm just saying I'm output the classifier smallest error rate over the sample. And for both of these classifiers, where true error rate is within epsilon of our empirical error rate. So what does it imply about the true error rate of the classifier that I output? I'm sure that if you write down on a piece of paper, you're going to immediately see it. So it's basically, right? So what I have is, okay, let me quickly do it, and that will be the last thing I'm doing, right? So the error rate, let's call H star to be the best classifier in the class that has the smallest true error rate, right? And what I know is that its empirical error rate is within epsilon of its true error rate, right? Right? I know this, right? And I also, because the number of samples was large enough, right? And let's assume that H is a classifier that I output, right? That had the smallest empirical error rate over the sample. But I also know that its error rate, true error rate, is within epsilon of its empirical error rate. And I know that basically the empirical error rate of this classifier here is smaller than the empirical error rate of the classifier H star. Right? So then what does it imply about the true error rate of classifier H as a function of the true error rate of the classifier H star? I claim it's not too much larger. Can you guys see what is the bound? Is it? Guess there's something that I didn't write here. So I also know that the empirical error rate of the classifier H is at most the empirical error rate of the classifier H star. Right, so I have two classifiers. The one that has the smallest empirical error rate, and so therefore, because it has the smallest empirical error rate, the smallest error rate over the sample, its empirical error rate is smaller than the error rate of the classifier H star, the best classifier in the world over the distribution. I know that for both of these classifiers, their empirical error rate, so for classifier H star, its empirical error rate is in epsilon of its true error rate, and similarly for classifier H. What does it mean if I use this effect? What do I get about the true error rate of H? Well, it's the true error rate of H, right, by using this fact over here. By using this fact over here, the true error rate of H is at most epsilon plus its empirical error rate. But the empirical error rate of H is at most the empirical error rate of H star, right? And so when I know the empirical error rate of H star is, if I do a chain, if I use these three facts and I go for a chain, then what do I get? It? The empirical error rate of H is at most the true error rate of H is at most the true error rate of H star plus, come on guys, please help me. Okay, do we have time? Okay, I think I'm almost over time, but I want to finish this point. Okay, so maybe I'll quickly do it. So anybody sees it? Okay, I'm going in the wrong direction. Well, okay, I'll just mention it. Plus 2 epsilon. Right, so I claim that if you couple all these facts, when you can get that if the number of training samples we see is at least this quantity over here, then the true error rate of the classifier output is at the true error rate of the best classifier in the class plus 2 epsilon. Okay? But that's great, right? Because it means that I can get generalization guarantees. Okay, and I'm done. Just want to mention that in the agnostic case, the main difference from the realizable case is the dependence on epsilon. Now it's epsilon squared as opposed to epsilon. So it used to be 1 over epsilon, now it's 1 over epsilon squared, but this is a much stronger statement. Okay, and I'll start from there next time. Okay, cool. And again, homework number 4 is out today, and homework number 2 grades will be released.